Good morning, students. Today we go to the next lesson of digital communication. In our last lesson, we concluded pulse code modulation, where, just to recap what we discussed yesterday, we learned that the original signal, the basic signal, which could be a speech signal or a song, it is passed first through an anti-aliasing filter. I hope you remember anti-aliasing filter. It's a low-pass filter which limits the bandwidth of the signal to a certain given value, say FM, so that the whole system is designed on a certain value of FM, maybe 10 kilowatts or so. So in case there is any frequency component above 10 kilowatts, that's going to disturb the system, and when the sound is reproduced, it's going to be noisy. So it is band limited to 10 kilowatts. That is the anti-aliasing filter. Then there is a compressor. You remember compressor, it's a nonlinear amplifier. It normally emphasizes the low amplitude signals, and it, I should not say de-emphasize, but it amplifies the low signals more than the high value signals. Then there is a sampler which takes samples. Then there is a quantizer which quantizes the samples to a certain number of steps, and then quantized samples are encoded to digital by a digital encoder, maybe a A to D conversion. That was pulse code modulation. Now, pulse code modulation is actually the basic principle of source coding, and then there are other more advanced methods also. The next method that we shall learn today is differential pulse code modulation, which is normally said DPCM, right? Now let's go back to pulse code modulation here. You remember that the whole signal has a range. Let's say plus minus 10 volt or plus minus 5 volt. And that range of plus minus 5 volt is divided into a number of steps, let's say 8 steps. So if plus minus 5, that means 10 volt is divided into 8 steps. Each steps becomes 1.25 volt. So at any certain step, whenever the signal is within the range of that 1.25 volt, it is given one particular value. But mind it, in that range, 1.25 volt range, there are many possible values, but they are quantized to one single value. So there are two ways of get out of this problem. One is either you increase the number of steps so that each step is small. Instead of 1.25 volt, maybe it is 0.5 volt, so that this error is small. Or what you can do, you decrease the amplitude of the signal. If you decrease the amplitude of the signal, then there is a problem. If the signal is decreased too much, then the signal becomes weak and it becomes difficult for the electronic system to handle it. So it is all a design aspect to what value of signal you design your amplifier, input signal, and how much steps you take for quantization, etc. So a method has been developed where you measure the sample. This is signal. You measure the sample MT, and then you measure, say this is MT1, Then you measure the sample MT2, but you do not quantize MT2. Quantize only the difference between MT1 and MT2. That is, the difference is delta T. That means the quantization input becomes very small. And obviously, if the sample rate is high, then the difference of last sample to present sample is very, very small, maybe a few millivolt, or may not be even maybe less than that. So this gives a benefit. Here, only the difference del T between the present sample and the last sample is taken as the information signal, right? Difference del T is sampled to a symbol del K, because del T also has a range, but if del T is within a certain range, it's given one value, and it is quantized to another symbol, del quantized T before transmission. So after the first symbol has been measured, first sample has been measured, thereafter what you measure is only the difference from the last sample, plus or positive or negative difference. And you quantize that sample, which is very small, and then you convert that small signal to digital signal. Now, these difference values are always very small in comparison to the sample values themselves. Hence, much less number of bits are necessary to maintain the same signal to noise ratio. If you want to maintain the same signal to noise ratio as the pulse code modulation, then here, since the magnitude of del T is always very small, so let's go to the earlier picture. Here, the signal range is so high. So there are 8 bits, right? If the signal range is very small, then maybe only 4 steps is sufficient. If only 4 steps are sufficient, then only 2-bit data is sufficient. If only 2-bit data you supply, then you are sending out or transmitting much less number of digital bits. That means you need much less bandwidth of the channel. You occupy much less bandwidth. That means you can save your money on the bandwidth of the channel while you are maintaining the same signal to noise ratio as the original pulse code modulation. So this is the basic principle of differential pulse code modulation. And at the receiver side, what it does, on the receiver side, it measures and keep in memory the first sample, and every second, third, fourth sample, it measures the difference. So from first sample, it adds the difference, it gets the second sample, and from second sample, it adds the difference, it gets the third sample value. So that way, the receiver reconstructs the entire signal. Now, let's see. This is the basic principle. Now, let us see the pros and cons. You as a student, let me tell you, for every such small items or issues, you need to remember only 2 things. One is, what is the basic principle of measurement? Principle. If there is a little bit of mathematics, you remember that little bit of mathematics, and you remember the pros and cons of this technique. Here we found a pros was it saves bandwidth. Then let's see what are if there is any negative side of it. Here, circuit is designed based on a assumed maximum possible del T. That means difference from one sample to other sample. For example, maybe somebody is singing and At one moment, he creates a high intensity sound, and the next moment, he creates a very low intensity sound. It normally happens in classical songs or classical musics. So, the design has to be based on what is the maximum possible delta. But let me tell you, so long as it is human voice and the samples are so fast, maybe a few milliseconds. So this is really not a problem for a human voice. It may be a problem for maybe a temperature transmitter or some other transmitters where signal may vary very suddenly and widely. Human voice signal does not vary so suddenly. Anyway, the design is based on an assumed maximum possible difference. Now, error occurs if the actual difference is more than that limit. Suppose you have designed a system that from one sample to other sample, the maximum difference is 1 millivolt. If by any chance the difference becomes 1.1 millivolt, then there will be a problem. But you can circumvent that problem. Possibility such error can be reduced by increasing the sample rate. If the two sample is more than 1.1 volt, more than 1 millivolt, then what do you do? If you take another sample in between, then definitely difference will be less, right? So depending upon what kind of signal you are handling, is it a human voice or is it the industrial physical transmitter or what is the expected rate of variation of the signal, you can change the design and change the sampling rate and you get this problem solved. Of course, further last it says, of course, quantization noise is always present. Because you remember, quantization noise is due to quantization. In pulse code modulation, you quantized the signal itself, so there was some error. Here you are quantizing a small difference signal. Again, there will be some quantization error, maybe a small value, but there will be error. This you have to keep in mind. Now, other aspects of differential pulse code modulation only accumulates the differences. Look, receiver is not getting what is the nth sample value. Receiver is only getting the difference between nth sample value and n minus 1th sample value. And there is a digital transmission in between. So, if there is an error in transmission and the receiver receives a wrong information and receiver adds up that wrong information to create the nth value, then all subsequent information will be wrong, isn't it? That is one major problem of this DPCM. Because if there is a error once, then this error continues. But engineers have found out some method to circumvent that possibility also, and at least to reduce such possibilities. What they do, they have designed a scheme like this. Now let us see what is the scheme. At the transmitter, see, let us see first the receiver side. This is the receiver side. Receiver side, when the delta signal is reaching the receiver with form, that there is a predictor. Predictor predicts what should be the value of delta. In electronics system, there are many such application of predictor circuits, which predicts what is the possible value. Because if you are taking sample values of human voice, and if you are tracking or sampling the voice for last 5 minutes, maybe 5 million samples you have taken, then it is always possible for a predictor to predict what should be the next value, with some, of course, plus minus error. On the receiver side, there is a predictor and there is an accumulator, another circuit. Besides, what is the receipt value of the sample, m dash k, receipt sample value. And then it uses a low pass filter to find out m dash t. The same predictor is used in transmitter side also. What it does, look, there is a MT, the input signal, then there is a last signal, this was the last sample value, and this is a subtractor which determines the difference del t. Del t is sampled. After sampling, it becomes quantized del k. Then after quantizer, it becomes del qk. And then the binary coder creates the binary signal. At when the del qk has been obtained, then this value goes to the predictor and then to accumulator. The accumulator decides what possibly is the next value. And that next value is again subtracted from here and the sample is created. Right? This eliminates the possibility of error due to del t shooting beyond the designed limit. Suppose at any particular, between two particular samples, as we said earlier, maybe difference between the two sample is 1.1 millivolt, but my design is 1 volt. This accumulator will give a signal of 1 volt, 1 millivolt, so that this possibility of shooting beyond the desired limit is removed, right? Then this is the same diagram of the last page. Now there are some conclusions, and you as a BTech student, you need not go into mathematical calculations and details of that, but you just have to remember that what are the, as I said, positive side and negative side of each technique of source coding. The pulse code modulation, let us see what are its properties. It has been observed that DPCM produces unacceptable quantization noise when sampled at the Nyquist rate 2 FM. That has been established. Some of you who know MATLAB programming, you can simulate this in MATLAB and see that if the baseband signal is band limited to 10 kilowatts and you do sample at the Nyquist rate of 10 multiplied by 2, that is 20 kilowatts, the quantization noise of DPCM will be very high. Very high. Forget about the mathematics behind it, it will be high. This noise can be reduced by increasing the sample rate. That means if you have a 10 kilowatt signal, then you have 20 kilowatt sampling rate, but instead maybe you sample it at 30 kilowatts or 40 kilowatts. If you increase the sampling rate, then the noise can be reduced. But problem is, the moment you increase the sampling rate, you are transmitting more digital data. If you transmit more digital data per second, then your channel bandwidth requirement increases. So, though theoretically is supposed to give less noise, but practically it has been found that if you want to really attain that noiseless transmission of DPCM, then you need much larger bandwidth than theoretical calculation. The reason behind all these things is the mm, randomness of the signal. You have possibly already learned random signal, stochastic signals, etc., etc. Because a human voice or anything, any natural signal is always random. You can predict to some extent, but you cannot predict everything. Second point, it has also been observed that if sampling rate of DPC so increased that signal to noise quantization noise is same as that as the plain pulse code modulation, the required bitrate is much larger. As we said earlier, it has been found that DPCM gives larger quantization noise, and if you want to maintain the same noise signal to noise ratio, you need more number of samples, and that means your bitrate will be larger. So this is what is said. The required bitrate is much larger in case of DPCM than in pulse code modulation. Then coming to the predictor that we discussed here, this predictor and this predictor. This predictor has the facility to memorize the past values of MT or del T and predict the next value of MT or del T. It's not a very sophisticated circuit. It is possible. Now, we have said about the noise, it needs more bandwidth, more sampling rate, etc. Now it says, predictor, DPCM can give comparable performance at half the sampling rate of PCM. You got the point? Above here, in first point and second point, we have said DPCM gives more noise, and to reduce the noise or at least to maintain the noise to PCM level, you need higher sampling rate, you need higher bit rate and higher bandwidth, etc., etc. But lastly, it said, if you use a predictor which predicts the possible next sample value, it has been found that half the sampling rate of pulse code modulation is required. That means that means the DPCM now wins over the PCM if you use a predictor. And if the sampling rate you can make half, then you save channel bandwidth, half of the channel bandwidth. That means if you have already purchased the bandwidth, then you can transmit two signals. You use it at two channels. Okay. Next, our lesson will be linear delta modulation. This is the third type of source coding, but that we shall discuss in the next lecture. Okay.